Hi, we are DGED. Today, we will be discussing the design of arithmetic logic units. Let's first look at a complete design of ALU. So it consists of two 4-bit multiplexer and one 4-bit adder subtractor and one 4-bit D flip-flops, which represent a register. Let's focusing on the adder subtractor. For 1-bit full adders, it takes 3 inputs, which are A, B, C in. And the sum is generated by 2 XOR gate, and the C out is generated by two input AND gates and one 2 input OR gates. So for 4-bit adder or subtractor, it is made using four full adders and 4 XOR gates. So the rectangular box right here is the symbol we created from the 1-bit full adder. So it is actually a 1-bit full adder. So the ALU operation is controlled by an inverter. So this inverter determines the functions of this design. So when the ALU operation is set to 0, the inverter will invert the 0, it becomes 1. And therefore, the design will perform a 2's complement operation for subtraction. Let's look at the waveform. So this is the waveform of the 4-bit adder subtractor. As you can see, when the ALU operation is set to 0, and when the input A is 1, 1, 0, 0, the input B is 0, 1, 0, 0, the result will be 1, 0, 0, 0. It shows that the design is doing subtractions, and it is added as a subtractor. And when the ALU operation is set to 1, input A is 0, 1, 0, 1, input B is 1, 0, 0, 0, the result will be 1, 1, 0, 1, showing that it is doing additions, and the design is added as a adder.
So to create our 4-bit 4-to-1 marks, we basically combine 4 1-bit 4-to-1 marks. So connected to the first 1-bit 4-to-1 marks is the first bit of each input. The second marks is connected to the second marks is the second bit of each input, and the third bit to the third multiplexer module, and the fourth to the fourth multiplexer module. So when S1 and S0 equals 0, it will select the first input, which is I0, and this will connect it all to the output through the bus line and form a 4-bit output. So let us look at the waveform. So this is our waveform for our 1-bit 4-to-1 multiplexer. So for example, if you look here, when S0 equals to 0 and S1 equals to 1, this in decimal will means 2. So it means that it will select input 2, and input 2 is 1. So that means our output equals to 1. And for our 4-bit 4-to-1 multiplexer, it's basically the same thing except that the output and the inputs are 4 bits.
Okay, right now I will explain the 4-bit D flip-flop that represent a register that we design. We can just simply implement the 1-bit D flip-flop that's provided in practice to complete this design. As we all know that the D flip-flop is an edge regular circuit. The output will only change once per clock cycle. During the clock rising age, if D equal to 0, the output here will be 0. And if the D equal to 1, the output will be 1. Since we have the reset input here, which will reset Q to 0 without a clock pulse. Let's look at this example. We got a clock rising edge here, and at this time, the D equal to 1, 1, 0, 0. And we should make sure that the reset is not equal to 0, since the reset input will set the output as 0, 0, 0. So we got a clock rising edge here, and D equal to 1, 1, 0, 0, so that the output will be 1, 1, 0, 0. We'll look at another example. The reset here is equal to 0, and the reset input will reset the output without a clock pulse, so the output will become 0, 0, 0, 0. Let's look at our overall design. The input here will produce in the 4-bit marks, and then the output will become the input to the 4-bit adder of subtractor. Then the output will continuously become the input in our 4-bit D flip-flop, and the output will be our final output, which is also 4 bits too. Now let's look at an example of waveform for our overall design. The A selected is equal to 1, 1 means we will choose the A3 as our input, which is 0, 0, 1, 1. And B selected equal to 1, 0 means we get a B1, 0, 0, 1, 0 as our input. And the other operation this time is equal to 0. So the adder and subtractor will add as a subtractor right now. And we get A3 to minus with our B1, 0, 0, 1, 1 minus with 0, 0, 1, 0. So that we will get 0, 0, 0, 1 as our input of D. And at this time, we got a clock rising edge, and the reset is not equal to 0, so that the reset input will be not function. And so our D is equal to 0, 0, 1 here, and so that our output will equal to 0, 0, 0, 1. As a conclusion, our design can be functioning well.